Welcome to the lecture series on computer science. In this series, this is a course on artificial intelligence, and as a part of this course, today we will be looking at module. Actually, we are in unit 2, and in unit 2 we are seeing the simulated annealing and constraint satisfaction problem. In the last session, we saw about local search algorithm, where I have described about the hill climbing algorithm. Continuation with this, today we will be seeing simulated algorithm, and in this I would have mentioned we would be seeing adversarial search as well as genetic algorithm, but genetic algorithm will be covered in the forthcoming sessions, and adversarial search will be covered after the constraint satisfaction problem. There is a small change in that schedule, and today we will be looking at first the simulated annealing as a part of local search algorithm, which is an optimization technique. Following that, we will look at the other type of algorithm, which is the constraint satisfaction problem, and the flow would be such that first we will look at a few real time examples, so that we would all be clear with what constraint satisfaction problem is, and this is actually a kind of a search technique itself. Secondly, we will look at the formulation of how to do it in the constraint mode, and there are certain types in it that we will look at it. Following that, we will also look at how to solve the constraint satisfaction problem using backtracking and other heuristic techniques, and along with that we will also look at the consistency approach, which would be the arc consistency and the path consistency type. Specifically, we will look at the constraint propagation in terms of arc consistency method. Now, we will start with the local search algorithm, and if you remember last time we did the hill climbing algorithm, where when we move towards the hill, if you look at it, it would be such that, say, in the hill climbing algorithm it would look, we will look something like this, where this is going to be the local optima and this is going to be the global optimal. And we also have solved some problem with respect to it. And if you remember, the solution to it is, at each stage we call this as a state S. At this point we will evaluate the neighbor, and the neighbor, it is going to be S dash, and if this S dash is better than this S, then we would make this S dash as the current state and move on. This is the flow with which we did the hill climbing algorithm last time, but there are some problems in it. The problem is the local optima. Suppose it can get stuck here. The reason is, after this it is going to be a fall. So, the algorithm thinks that, okay, this is the answer, and it just spits out the answer at this point, whereas the real answer is like right here, or it might be right here. Okay. Or suppose we start here, it would say this is going to be the answer and it will fall off. It will say that this particular point is going to be the answer, which is not correct. This is going to be, in this case, the global optimal, okay, and this is again the local optimal. And remember, it is again monotonously increasing or monotonously decreasing, and in this case we are seeing the monotonously increasing graph. Simulated annealing is an extension of this hill climbing algorithm, where the name itself is got from the annealing, the inspiration from annealing. In annealing, what they do is, materials are heated onto a specific temperature, and that temperature would be a very high temperature, let us say T is greater than 100, and from that temperature it is made to cool to reach to some stable state. And with this inspiration, what we are going to do is, we will calculate the neighbor value, like very similar to that of hill climbing algorithm, and if the neighbor value is going to be worse in the sense, suppose there is a local optima. In the hill climbing algorithm we reject, but in this case we will not reject, but accept with some kind of a probability. So, this is the intuition behind that simulated annealing. We will look at the algorithm, and following that an explanation of it. Okay. The algorithm goes like this. So, remember this is a hill that we are seeing, where there is going to be the initial state or some random state, and S dash is going to be the next neighbor state, S and S dash right here. So, initial the current state S and set an initial temperature T to a very high value, which is similar to the annealing temperature, and we are going to repeat these steps. Generate a random state S dash, which is similar to this. So, compute S dash and compare S dash minus S, that difference is delta E. If delta E is greater than 0, then we will make S dash as the current state. This is going to be the current state, this is no problematic case. But if delta E is less than 0, it is worse, then move the neighbor with the probability of it. We are not going to reject, but we will accept it with some kind of probability. And continuing with that, what will happen to the temperature? Now, we have accepted that probability, but slowly we will reduce the temperature. If the temperature reaches a small threshold, then we will stop it, and by the time the advantage is it might reach a global maximum as we aspire and stop at that, and it might give a correct answer. So, this is a optimization problem. Now, we will look at an example. Let us say, and this is the intuition with which we started, if the neighbor value is worse, do not reject, but accept with the probability. If delta E is greater than 0, it is accept, which is no problem. If it is less than 0, we have to evaluate this expression exponential delta E by T, and remember delta E is nothing but the difference between S and S dash, the neighbors. Now, consider the change in state as, suppose I will give you 5 different conditions what will happen to these values. So, let us say if this difference delta E is minus 10, where there is a small change in value, and remember when there is a, suppose the delta, this is S and this is S dash, there is no problem, which constitute delta E is greater than 0. The other case is what we are now looking at. Suppose if it is S and the other point is S dash minus S, it is going to be negative, and this negative, how big this negative is, that is what we are going to see in these. Suppose this delta is minus 10, this is minus 10, then this expression, suppose if the temperature is very high where we have kept 100. So, the denominator here is 100, this is minus 10, this probability is evaluated to 0.95, which means we can accept it and move on. We can make S dash as the next neighbor. See, in this hill climbing algorithm, S dash will be rejected, but in this case, based on this probability, this is going to get accepted. And this is the second case. Suppose the temperature, the same value of minus 10, this remains the same, but the temperature is 0.368, this case, then it is low acceptance. So, we have a low acceptance and we can decide whether to accept this state or move or reject it. Third case, where this difference is going to be minus 1 and with a high temperature. Remember, this is minus 1 and this is a high temperature, the probability is 0.99. So, accept it highly. If it is going to be minus 1 with the temperature 1 degrees, then it is 0.368, a low acceptance. So, the probability of rejecting the neighbor. So, this is how simulated annealing is proceeding. So, that at the end we would be seeing whether to accept the neighbor and or to reject the neighbor, so that an optimal solution is attained. And here is another example where minus 20, this is the worst case where S dash is somewhere here, it is minus 20. With a temperature 10, it is very low acceptance, we can straight away reject that. This is an example of local search, and with this we are completing the local search with 2 algorithms. One was hill climbing and the other one is simulated annealing. The third type, which is the genetic algorithm, I will in the forthcoming sessions. The next topic we are going to do is a constraint satisfaction problem, another search technique where it is a different problem where we have some constraint. So, first we will look at 3 examples, the real life examples, so that we can understand what the constraint satisfaction problem is. Say in example 1, we have a map coloring problem. For example, if you see in the left side, this is a map of Australia with the states Western Australia, Northern Territory, South Australia, Queensland, New South Wales and Victoria and Tasmania. The idea is we have to color this Australian map with 3 colors, red, blue and green, such that no 2 adjacent regions share the same color. So, it is very similar to the graph coloring problem. The solution here is, this is the solution, with red, green and blue we can color the adjacent regions such that no 2 adjacent regions are going to share the same color. First example. Coming to the second example, this is a crypt arithmetic puzzle that you might have solved when you are young. It goes like this. We have 2 words that are coming here at the top and bottom. Here it is that represents actually the integers TWO, TWO. The idea is we have to assign each value for each character a value of an integer such that it is not getting repeated, meaning we have T, W, O, F, U, R. For each of these characters, we have to assign some numbers, positive numbers, such that it should be unique. Okay. So, how do we do that? So, assign using unique integer values to each of the characters. One of the answers is like this. It would be T is corresponding to 9 and W will be corresponding to 3, O value can be assigned as 8, F 1, O is again 8, U is 7, R is 6, meaning when you add 8 plus 8 16, 3 plus 3 plus 1 7, 9 plus 9 18, you get this. Okay. So, when you have this crypt arithmetic puzzle, how do we solve it? So, we can solve using this puzzle is we can solve using our brains, but how do we ask the machine to solve it? So, this is the second type of problem. The third example that I have put is a job scheduling problem. The scenario here is the real time manufacturing plant job scheduling and very similar to our CPU scheduling also. The objective is minimize the total completion time. Assume we have 3 machines for this case. Suppose you have M1, M2 and M3, 3 machines and we have 4 jobs J1 to J4, 4 jobs and each one takes some time, particular machine. Now, how do we optimally complete all the jobs in a minimal time using these 3 machines? That is one type of problem, the schedule called as a scheduling problem. Another similar problem is our timetable scheduling, like I am taking this class for you and the need is the classrooms, availability of time, availability of certain instructors and availability of students. So, based on so many constraints, how do we schedule the classes? So, these type of problems mapped into this constraint satisfaction problem, shortly abbreviated as CSP. So, so far we have seen 3 problems. One is the coloring problem, second one is the crypt arithmetic puzzle and third is the job scheduling problem. So, I have given a brief overlook of what CSP is all about. Now, how do we do that using a machine? How do we solve it? Okay. For that we have to formulate it. We have to formulate such that a machine can understand this stuff. Normally, the formulation goes in these categories. we will describe in terms of the variables as x. X is starting from x1 to and n is right now we are going to take it as a discrete. The second is the domain, D is D1 to Dn, and on the right side you can see the example of Australian map. We will map all these, we will consider all these variables and domains into this map now. The third formulation is the constraint, which is given in the form of scope and REL, which stands for the relation. The scope within the variable side and the relation generally describes the values, whatever the values with the variables. We can describe that in the form of constraint. I will give you an example so that it would be clear now. For this example of the map coloring problem, the variables are the states. This is Western Australia, WA. Western Australia is abbreviated as WA. This is NT, Northern Territory, Queensland. This is Queensland. This is South Australia. This is New South Wales. And Victoria. This is Tasmania. So, the variables here are the states. The domain, here we are going to have the three colors. The idea for this map is no two adjacent regions should share the same color, that is taken as the constraint. Here we are mentioning as WA, which stands for Western Australia, should not have the same color as Northern Territory, these two. So, that we can represent as WA not equal to NT. That means, the color that we have in WA should not be the same as color in NT. So, this is the first formulation for this example. Okay. Before we move on to the second example, one solution is this, having these colors WA. What is the solution for CSP is, for each variable that we have described, assign a value from this domain to this variable, that is going to be the solution. For example, for each of the variable WA assign red, for NT assign green, for Queensland assign red. So, this is actually the solution to CSP. Now, moving on to the second example, we saw this crisp arithmetic puzzle, where the variables here are going to be the characters, where we saw F, T, U, W, R, O, and this x 1, x 2, these x 1, x 2, x 3 stands for the carry. The domains are going to be the values that we are going to assign to each of these variables. The constraint is all diff, meaning for this example, each of the value that we assign to the variable should be unique. Therefore, we have a function called all diff. So, we can program it such that whatever the values that we assign from this domain to f, it should be different from all these. Whatever, similarly, whatever the values that we assign from one of the values from these domains to t should be different from all others. Okay. So, that is the meaning behind this all diff. So, this is how it goes, and how to solve it. Right now, it will be O plus O will be R plus 10 times this x 1, x 1 is the carry, and this x 1 plus W will be U plus 10 times x 2, and this x 2 plus T would be O plus 10 times x 3, and x 3 is f. Since there is a left portion is 1, we will say okay, f has 1, and then we will compute the remaining stuff. Okay. But how the would go is, the solution is we will be assigning each of the values to the variables and all the such that everything is going to, all the values that we are assigning is going to be unique. So far we have seen the three examples in CSP, and secondly the formulation in terms of variables, domains and constraints. So, in CSP the first thing we have to do is consider variable, domain and constraint, just put it in this format, and once we have put it in this format, the next step is we can think about the solution, how to solve it. Okay. And before we go into the solution mode, we will see the different types of CSP. See, we have already said there are three things. One is variables, domains and constraints. Now, in the variables itself, we can see discrete variables. Whatever the example that we seen so far are discrete variables, where the domains are of size d, and this is obviously going to be in the order of d power n. And there are also infinite domains, like for example, integers or strings. This can go on and on. The other portion is the continuous variable, and for the continuous variables, it would be in the form of sum less than or equal to, sum x 1 plus x 2 should be less than or equal to 100, something like this. So, to solve this continuous variable, we will be using a linear programming model, but for this course and whatever we do today and for the next session probably, we will focus only on discrete variables with finite domains. We will only focus on this stuff. Okay. Now, when we talk about the constraints, there are unary constraints, like for example, if you take the Australian map, SA should not be green, that can be given as SA is, this is the variable, remember, and this is going to be the color from domain. This is an example of unary constraint. Now, binary constraint is between two variables, both are variables. This is an example of binary constraint. Similarly, there are ternary constraint or higher order constraint, where it will involve three or more variables. The example we saw is the crypt arithmetic puzzle, where the constraints here is going to be more than 2 or more than 3, right. So, for example, whatever value we assign to f should be different from all these. So, it is going, this constraint is coming under the higher order constraint. So, this is the second type, which would be based on the constraint. Now, before going into the solution, we have to understand how to represent it as a graph, and why do we want to represent it as a graph? Because that would make us easy to solve a problem. Okay. And any constraint that can be higher order constraint can be converted into a binary constraint. For simplicity, we are taking the same map of Australia here, and we have converted into a graph, this graph. And here if you see, the state are represented as a node. All these are going to be the state of Australia as the node in the graph, and the edges represent the adjacent region. The edge is going to be the adjacent region. So, this is an example of a binary constraint. The binary constraint, this is a binary constraint. Why? Because this arc is supported with this node of W A and S A. So, if we assign red to S A, W A should not be red, this should not be equal to red. So, the idea why to convert this to a graph. So, having all this, we will talk about how to solve this problem in a systematic manner. Okay. And we are doing only a simple search technique. If you remember the search, we have a node, you do some operation, you go to the next node or next state, move here until you reach to the goal. This is our simple state diagram. You start from some state, go through BFS or DFS or some method until you reach to some state here. This is the NSN, which is going to be the end goal. Now, our CSP problem is going to work in a very similar way, except that at this point we will have the assignment of solution. assignment of each, see at this line, this is the leaf, at leaf level we will have the solution to the constraint satisfaction problem, where for each variable we are going to assign the value from domain such that the constraints are obeyed. Constraints are obeyed, that is going to be our goal. Now, for this we are going to use the backtracking approach. A backtracking approach is, if you look at this function, okay, this is a recursive function. If you look at this, the backtracking approach, where it will start with initial assignment, just assignment from the domain. It will get into this variable called var, and if it is consistent with assignment, meaning if it is obeying with, if that constraint is obeying with that variable, then we will assign it and move on. But if there is a failure, it will again go back to this backtrack and do again and again. So, this is a recursive function. So, we will go through this algorithm with an example, again come back to this algorithm. Say suppose for example, we have 4 regions A, B, C, D. Just for simplicity, I have chosen just 4 regions A, B, C, D, where A is adjacent to B, B is adjacent to C, and C is adjacent to D. Okay. And like a similar map coloring problem, we have to color each of the regions with 3 colors. So, at the first stage, we are choosing A. At this stage, this corresponds to, at this stage, select unassigned variable. At this stage, I can choose any color. So, I am taking A, choosing A and coloring red, and because it is obeyed, the variable will store here and will go to the next one. And remember, first it is going to take in the depth first route. So, in this place I can again color it as B, but having A and B, no 2 adjacent regions should share the same color. So, this actually there is a conflict in this assignment, which corresponds to there is a failure. There is a failure. So, it will again go back, this is the backtrack, it will go back and this recursive process will go to this state and take the other color from here. So, this is a simple backtracking approach. So, what we do is just use a depth first search, and if there is a conflict, use the recursive approach to the next stage. Now, this is a backtracking approach, and the key points of this search is, it is very simple as we have seen earlier, okay, but it is slow, and when the problem size is large, it becomes very slow. The another advantage is, it is backtracking, it can lead to a early failure detection, which is not possible in other cases. But if the problem size is large, the search space is n factorial d power n abilities would be there in order to find out the search space, which is extremely huge, which is difficult. How to overcome it? We can use some optimization heuristics like minimum remaining values or least constraining values, and other techniques such as forward checking, which can be combined with other minimum remaining values. And another approach is constraint propagation method, where we can use AC3 algorithm, which we will be doing in the next session. A summary: in this session, we have seen first the local search algorithm, which is the simulated annealing, where it is an optimization technique. So, what we do here is, at first we the high temperature, so that we can accept the neighbor and then gradually reduce it, and through this method an optimized state is being returned. Secondly, we saw the CSP technique, where the constraint satisfaction problem involves the 3 formulations of variables, domain and constraint. Here the solution is such that we have to assign a value from the domain to the particular variable, such that the constraints are going to be obeyed. Now, that is the solution, and there are some varieties to these CSP in terms of the variables and constraint, and in the variables there are specifically two types of variable, one is the discrete, another one is continuous. In this session or in this course we will be looking at only the discrete and finite variables, and the constraints we talked about the unary, binary and higher order constraint. There are some examples to it like map coloring which we saw, pseudo queue that you normally play, the job scheduling problem or the n-queen problems. So, those can be solved using the CSP techniques. To solve this using a machine, we have several methods like backtracking, where we saw the algorithm now. There are also other techniques like forward checking with the minimum remaining value heuristic, the degree heuristic in terms of graph, and other consistency methods like the arc consistency. For that we will be using AC3 algorithm. In the next session, we will be covering these solution methods, specifically the forward search with MRV, the AC3 algorithm and the adversarial search.